All right. Once again, just a reminder that you are being recorded, or the session rather is being recorded. Your names will not show. Anything you type in the chat will show, but it will be anonymous. So if you want to review this session later, you can on our YouTube channel or through e-learning. Okay. And for those of you who are joining later, asynchronously, today we're going to go over any past topics and answering some questions, as well as starting to get into isomers, stereochemistry, maybe chair conformations as well. Okay, so the first question is how to know what orbital a lone pair is in. Okay, so I'm going to use this example. I believe you guys should be familiar with this structure. It was in a practice quiz. Okay, so remember in organic chemistry, they don't show any of the hydrogens or the lone pairs. So you have to remember the standard lone pair to bond ratio, which once again, carbon has 4 bonds, no lone pairs. Nitrogen has 3 bonds, 1 lone pair. And these are ideal situations. Obviously, there are exceptions. Oxygen has 2 bonds and 2 lone pairs. Okay, so these are your ideal scenarios. So looking at my structure here, I have several carbons, 2 nitrogens, and 1 oxygen. I don't need to worry about adding lone pairs to my carbons, so I'm going to add 1 lone pair to my nitrogens and 2 lone pairs to my oxygen. Now that you figure that out, you have to identify the orbital each lone pair is in. But before we do that, we want to identify the hybridization of our 3 atoms, okay? And we can do so by counting the electron domains, okay? So this one has 1, 2, 3, 4 electron domains. And anytime you do hybridization, check for resonance. Check for resonance. This doesn't have any resonance, so this lone pair is in the sp3 orbital. So that would be the answer for this lone pair, N1. Now, these 2 lone pairs, once again, if you count your electron domains, this oxygen only has 3 electron domains. And technically, we'll get into it, but this can resonate. But ideally, you want to have, you want to state the orbital the lone pairs are in the lowest form of energy. So technically, this will resonate from sp2 to sp3 using this lone pair. But however, sp2 is less, requires less energy, so we're going to favor that. So as a result, the lone pair here are gonna both be in sp2. So this one's sp3. These 2 are sp2. And then last but not least, this nitrogen, it looks like it's in sp3, but once again, remember that you have to take resonance into account. So this lone pair, it can resonate here, but it can also exist on the nitrogen. So if a lone pair can resonate, it typically means that it's going to be in an unhybridized p orbital. Okay. So this is, for this one, it's a p orbital. Okay. And I can go further into detail on how I got p orbital. So if you still are confused, let me know. Okay, someone said if there is resonance, it's just p orbital. I don't particularly like saying bold statements like that because organic chemistry is very relative. But from what I've seen, for the most part, and it's mainly just this example, I do want to say yes to that question. Yeah, if it can't resonate, it cannot be in a unhybridized p orbital. But so yeah, if it can't resonate, just look at the hybridization of the atom it's contained on. Someone said, how do you know this lone pair is in p orbital again? I know it's in the p orbital because this lone pair can resonate with this double bond. And if it can resonate, this nitrogen automatically becomes sp2. It goes from sp3 to sp2. And then because it's an sp2, this lone pair is considered delocalized. Well, okay, someone asked why couldn't the first lone pair on this nitrogen not resonate? So it's simply because this lone pair is not close enough to the double bond, whereas this lone pair is close enough. Okay, it has to be exactly 1 carbon away. Okay, treat your lone pairs as negative charges, which that's what exactly they are. So imagine a negative charge on nitrogen or some atom 1 carbon away from your double bond. That indicates that you can resonate. Whereas this nitrogen with its quote-unquote negative charge is too far away. It's 2 carbons away from the double bond. Okay? All right, so once again, these electrons are considered delocalized if it can resonate, meaning it can exist in 2 different locations. And when it's on the nitrogen, it is in a unhybridized p orbital. Okay, and I kind of get into this in the previous sessions, so you might need to search for it in more detail. Okay. So that's all I'm going to talk about for that. If you have more questions, I'll try to answer them at the end of the session if we have more time. If not, I would recommend just going back to my previous review sessions. Okay, and then the other questions are ranking basicity and stability of chair conformations. Okay, chair, we're going to get to that much later. Ranking basicity, I would say for the most part, sorry, I'm going to clear this page. If anyone needs it, let me know. Okay. So ranking basicity is very similar to ranking acidity. The general advice a lot of people give is to rank by acidity and then flip it for basicity. And to rank by acidity, we use this method called ARIO. Can you guys let me know if you guys have seen this before, and if you guys have worked out a problem using this method? Just let me know yes or no in the chat. Okay. Someone said yes. Okay. Okay. I'm going to quickly go over this actually because I do think it's important, and I don't believe I've fully gone over it. I might have introduced the topic, but I don't think I've fully gone over it. So I'm going to do a full blown out example, and this is going to be a ranking by acidity question. And some of these principles directly apply to ranking by basicity. In a sense, you kind of just reverse it. So maybe this could answer and help you guys on your quizzes and upcoming exam. I also want to briefly mention to remember your periodic table trends. In OChem, you just have to worry about 4. It's basicity there and acidity here. and electronegativity here. Okay, and then we'll talk about the fourth one in the bottom left corner much later. Yeah, so essentially as you go up and to the left, you get your atom becomes more basic, and as you go down and to the right, your atom becomes more acidic. So between carbon, nitrogen, and oxygen, let me quickly write those. Oxygen is more acidic and carbon is more basic. And then if you want to look at the atoms right underneath it, silicon, phosphorus, and sulfur. Sulfur is more acidic than oxygen, and oxygen is more basic than sulfur, okay? Simply because it's closer as opposed to acidity. Okay? All right, so let me see. Once again, A stands for atom, R stands for resonance, I stands for inductive effects, and O stands for orbital. Within atom, I am specifically talking about the size of the atom, not electronegativity. Resonance, we just see yes or no. Resonance equals good for acidity. And inductive effects, we are looking for both location and strength. Okay, and orbitals, the simple one. It's just Fp is greater than Sp2, which is greater than Sp3. For basicity, it's the opposite. Okay. You don't necessarily get into orbital much. You shouldn't see that many examples, but if you do, and those are the trends. Okay. Now I'm going to give you guys an example that we can go over. Give me 1 second to draw all these. Can anyone remind me when your exam is? Or if you guys have an upcoming quiz? Okay, you guys have a quiz on Thursday. Do you guys know what the topic is? Is it about stereochemistry? Chapters 1 through 3. Okay, so for this quiz on Thursday, there shouldn't be any chair confirmations, correct? Okay. I'm sorry, this should be a carboxylic acid. Chapter 3 is alkanes. Chapter 5 is stereochemistry. I'm guessing chapter 4. Okay. Well, let's make sure your basics are good, and then if we have time, we'll get into chair confirmations. All right. Okay, I don't have space, but I'm gonna do. Yeah. Okay. Actually, that's all I'm gonna do. All right. So for all of these, I'm gonna quickly run through it. Atom, when I say, okay, before anything, any acidity problem, they always ask you to rank by the conjugate base, okay? And you can turn an acid into a conjugate base by donating its hydrogen, okay? Specifically the most acidic hydrogen, okay? Which is usually going to be one of these, okay? And not a hydrogen coming off your methyl or CH2s, okay? So we are going to place a negative charge on all of these atoms. Okay, that should be your first step. And if this is basicity, you would do the opposite while adding a hydrogen and adding a positive charge instead. Okay, now that you got that, I am going to write down the atom for each of these. Okay, so the first one, I have a O negative, S negative, O negative again, O negative again, O negative again, and O negative again. Okay, so we have lots of oxygens and one sulfur. Okay, based on just atom, you might be inclined to say sulfur is the one that has sulfur is the most acidic. But we can't solely look at the atom, we have to look at resonance as well, okay? And resonance actually trumps atom, so this is the most important factor in determining what is the most acidic molecule, okay? So for resonance, all I'm going to say is yes or no, or actually I'm just going to say a check mark where there is resonance. Okay, so this one has resonance and this one has resonance. Everything else does not have resonance, okay? Any questions so far? Okay, so based off this, we can actually answer or start ranking two of these, okay? Like I said, resonance is the best acidity stabilizer, okay? Or it makes things more acidic, okay? And because these two have resonance, they automatically become our 1 and 2, okay? Now, any guesses on which one is 1 and which one's 2? What do you think the difference is? Left one is 1, okay? Someone said left one is 1. Any other opinions? Or does anyone agree with that? Okay. I got one agree. All right, yeah, you guys are right. And it's because when you resonate this negative charge, it resonates onto another oxygen, okay? Whereas here, you go from an O negative to a carbon negative, okay? And if you guys remember from chapter 1 or the very first week or two, carbon does not want any kind of charges. We want to keep carbon happy, okay? It is the subject of carbon, okay? Because of that, this is going to be more stable because oxygen is more electronegative and it can carry that negative charge better. So as a result, our answer is going to be 1 here and 2 there. Next, we have 4 more molecules left and we have to figure out everything else, okay? Now, before we get into inductive effect, we can look at atom again, okay? And out of our remaining 1, 2, 3, 4, this is the biggest in size. So this one becomes number 3. Now between our remaining 3, 1, 2, 3. Yeah, resonance does make things more stable. That's why these were our... So, okay, so why would it want to be acidic? Stability and acidity kind of fall under the same like umbrella. Sometimes when they say most acidic, they also mean most stable. In this case, why would that be 3 and not the one with fluorine or chlorine? Okay, yeah, I'll get to that. So that does not mean basicity is not stable. It just depends on what they're asking. This question will say rank the following acids, number 1 being the most acidic, and it stabilizes everything, and resonance helps both acidity and basicity. So because it's good for both, actually I need to double check if resonance is good for basicity, because I'm not 100% sure. But for acidity, I would say resonance is good. Yeah, actually, yeah, you're right. Resonance does make things less basic, so resonance is bad for basicity, but good for acidity. So yeah, pretty much like the opposite of all of these for basicity. Right, okay. It's good because you're stabilizing this negative charge, and when the H leaves, you these are your conjugate bases, correct? But originally it was your acid, and the conjugate base, regardless, right? So you're essentially stabilized conjugate base, but like you're like quote unquote like still ranking by acidity, even though it says conjugate base, and stabilizing this negative charge and making it less unstable with resonance and size of atom kind of helps it. I feel like there might be a textbook explanation for why stability and acidity go together, or it could be in your PowerPoint as well. All right. So I'm gonna move on. Someone else asked, why would this be 3 and not the ones with fluorine or chlorine? So fluorine and chlorine directly go under what is called inductive effects, and this is when we talk about electronegativity instead of an atom. Atom, we strictly want to look at the size, not electronegativity. Inductive effect is when we look at electronegativity. And more specifically, this includes halogens. Okay? Now, the reason why this trumps it is because a bigger size of containing this negative charge is a more stabilizing than having halogens and electronegative withdrawing groups pull these electrons. Okay? Inductive effect essentially means that this negative charge is getting sucked in by this fluorine and this chlorine. Okay? So it makes this negative charge smaller. Okay? But here the sulfur has an overall bigger size, and it spreads that negative charge across its whole surface area. That's why it trumps it. So if you want some kind of order, it would be resonance, and then atom, and then inductive, and then orbital. Okay. Now, between our two inductive effect molecules, I talked about location versus strength. In this case, they're both located in the same carbon, so we are comparing strengths in this particular example. Fluorine, as you know, is the strongest or most electronegative atom, so it has a stronger, like it has a bigger arrow, or I guess 2 arrows. It has double the power as chlorine, okay? So it makes the charge even more minuscule compared to this negative charge, okay? And now location is, and anytime I talk about inductive effect, think about like magnets. So if you were to compare fluorine right there compared to fluorine further away, which one do you think would be more acidic? Fluorine away from the negative charge or fluorine closer to the negative charge? Just say left or right. Okay, someone said left and someone said right. Okay, so the answer is actually, okay, I got another right. So yeah, the answer is actually right. Like I said, think of these halogens as magnets and think of these negative charge, the ones that they're attracting to. Okay, so if your magnet is closer, you're going to have a stronger attraction and it's going to minimize that negative charge much better. Okay, but if your magnet is all the way here and further away from your negative charge, it's not going to have a stabilizing effect as it could while right next to it. Okay, does that make sense? Whoever, okay, all right, perfect. So once again, inductive effect, this is comparing location and this is comparing strength. Okay, so both of those are important. The closer you are, the better your inductive effect is, and the stronger your electronegative atom or halogen is, it makes it more acidic. And then once again, orbital, I just talked about it, sp, sp2, sp3 for acidity, and basically it's the opposite. So basicity, I would just flip all of these. Okay? All right. Any questions on acidity or basicity that I haven't answered quite yet? Okay. Yeah, if you have class at 2:30, feel free to go and then join us back. All right. So is anyone still copying, or can I clear the screen? Let me know now. Oh, right, yes. I apologize. Okay. Yes, so this would be number 4, number 5, and then the one with no resonance, no inductive effect, and then the smaller atom, it's going to be last, and it's going to be 6. Normally you only deal with 5, but I wanted to show both of fluorine and chlorine to show the comparison. All right. Any other questions before I clear this whole board? Okay. All right. So, someone says stability of chair conformations, but have you guys talked about chairs more or isomers more? And which one do you guys want me to cover? Because I feel like we should cover. Okay. I'm going to start with isomers because it's very straightforward, and then we can get into chairs. All right, so clearing the board. Okay. Give me 1 second. All right, so isomers, have you guys talked about chirality? Or have you guys heard of that term before? Let me type it. Okay, perfect. All right, so if this is new, or you guys are still confused on what chirality means, this would be a great first impression. So chirality means it has to deal with carbons, unique carbons specifically. So let's say you have a carbon here, and carbon has 4 bonds, right? So each of these 4 bonds has to be unique. Okay, so unique set of groups. Okay, it can be the same atom, but beyond that, it could be different. So you have to not only look at a single atom. Okay, for example, like I might have a methyl or like a carbon here and then like a isopropyl here, and then I might just have a single methyl here. Okay, even though these two are the same carbon to carbon, this whole as a group, the red is different from the orange. Okay, so if I see something like this, and then maybe I'll add like a hydrogen in purple, and then in green I'll add like chlorine. Okay, so if you notice, all 4 chlorine, hydrogen, methyl, isopropyl, okay, they are all different, correct? If they are different, this carbon is called a chiral carbon, and I'll write that down. So this carbon is considered to be chiral, and we name it as chiral carbon. Okay, chirality is like the subject or the topic. Okay, and then to give you guys some examples, so just a quick refresher. If you see that, that is called a wedge, and if you see this, this is called a dash. Okay, and that is important for chirality and stereochemistry and all of your Chair, Newman, and Fisher projections. You'll probably learn about that in the upcoming week. Okay, so I'm trying to give you guys an example of this. So let's say I have a bromine here. Sorry, that should be a Br. And then let's say I have a oxygen here. Okay, can anyone tell me, looking at this structure, how many chiral carbons there are? And then just type in the chat the number. Okay, someone said 2. Any other guesses? Okay, another person said 2. Okay, so yes, you guys are correct, and I will draw, or I'll put a dot, or I'll circle it. Okay, so these 2 are chiral because they contain 4 unique bonding, while all of these carbons don't have unique 4 bondings. Okay, So any methyl group or any like CH2 group, and make sure when you refer to this specific carbon, you don't say ethyl, because ethyl is not just one single carbon, it's like this whole two carbons or this whole two carbons. Just say CH2. So any CH2 or CH3, anything that has more than one of the same structure, like two hydrogens or two methyl groups, is not a chiral carbon. And even this, yeah, there are no chiral carbons here because these have three hydrogens, and this only has three structures or three bondings. Okay, if it has three, then it can't have four unique, right? It has to have four unique bonds. Okay, same for, you know, the triple bond carbon. So any double bond or triple bond carbons cannot be chiral, they have to be single. And once again, just because I put the bromine here as a wedge, that automatically means that our fourth bond that I didn't draw, and they won't draw this, or not always, you have to assume it's a hydrogen, and you have to assume it's a dash, okay? But if I flipped it and put the dash on a bromine, then our hydrogen would be on a wedge. You will always have one of the other, and not two wedges or not two dashes. Okay, any questions so far? There's still a lot more to cover, but is everyone still with me? Okay. So that's just part of the. Okay, so someone asked, so if you have a wedge, you have a carbon by default. I mean, usually, well, not by default, but like usually, they are bonded to carbons. Yeah. And it will show you in the, it will draw out what it's bonded to, so you can see. You don't necessarily have to guess, but from what I've seen, yeah, it's carbon. It's bonded to carbon. I haven't seen any wedges bonded to. Oh, okay. Not. I mean, hydrogens, yes. By default, there's always hydrogens around. If I only place one wedge for bromine, but let's say I do the same thing. One sec. Let's say I do the same thing with bromine as a wedge, but I indicate the dash is actually a chlorine. Then there are no hydrogens. But if I don't indicate, yes, please assume that there is a hydrogen and it's going to be on the opposite to what your bromine is. So if your bromine's on a wedge, you're going to have a dash hydrogen. If your bromine's on a dash, you're going to have a wedge hydrogen, if there's no fourth bond right here. If it's already noted for you, then that's how it is. All right, so the second aspect of this, you have to rank all of these structures, groups, by weight, okay? And you assign a number, once again based on weight. So out of chlorine, hydrogen, methyl, isopropyl, which one is the heaviest group? Okay, chlorine is the heaviest group, and then after chlorine, it's going to be isopropyl, and after isopropyl, it's going to be methyl, and then after methyl, it's going to be hydrogen. Okay, hydrogen is almost always going to be number 4. Have any hydrogens, then you would have to find your least heaviest group. Okay, once again, I want to emphasize group and not atom, because even though this is carbon to carbon, after that carbon, you have to see what else is bonded to it. Okay, so going back, we prioritized and numbered by weight, and we are actually going to draw a arrow to indicate the direction, and the direction should always be either clockwise or counterclockwise. Okay, in this particular example that I drew, this is clockwise. Okay, and if it's clockwise, it's called, we denote it as R. And if it's counterclockwise, we denote it as S. Okay. So, another aspect to this, sorry, give me 1 second. Is everyone still with me? If you guys are confused or lost, let me know. Okay, so once again, the three, I guess, rules or checklists, you have to see if the carbon has 4 unique bonds. Okay, and then, so let me check this out. To find chirality, one, find carbons that have 4 unique groups. Okay, groups, not atoms. Okay, and then rank those 4 groups. Weights. Okay, so once again, and when I say weights, I mean by, you have to go by single atom to atom. Okay, so for chlorine, I'm comparing chlorine to the single carbon compared to the single carbon. Okay, not chlorine and the whole isopropyl and the whole CH3. Okay, and we'll get to the specifics much later, but for now, just know that's by single atoms. And then last 3, determine if the sequence is R or S. Okay, and then you can determine that by looking at if it's clockwise or counterclockwise. So once again, R is clockwise and S is counterclockwise. Okay? All right. Next, we have to understand what happens, or make sure, like our 4th group, there are special scenarios depending. Right now, we're only dealing with single bonds, or I haven't put in dashes or wedges, but you'll have a lot of dashes and wedges on your chiral carbons. So for the 4th group especially, if it's on a dash or a wedge or a line, if it's on a dash, you keep. If it's on a wedge, you flip. And if it's on a line, you rotate. Okay? What I mean by this is, let's say your 4th group is, you determine your group and then you figure out your chirality, and the chirality ends up being R. If it's R, you keep it as R. Okay? But if your 4th group is on a wedge and you realize it's R, you have to flip it to S. And then if your 4th group is on a line, it does not necessarily mean keep or flip. You have to rotate your structure until you get your fourth group on a dash or a wedge, okay? And then if you rotate and it ends up being on a wedge, then you have to flip. If you rotate and it ends up being on a dash, you keep it. And I know that's confusing right now, which is why I'll do an example. But yeah, anytime they ask for chirality, they're asking to label R or S onto specific chiral carbons. Okay. I'm not sure how much of this is new. Has anyone covered any of this information so far, or is this all new? Okay, it's new. All right. All right. No, that's fine. Even though chairs are a little bit confusing, I feel like this stuff, chirality, could also be a little bit confusing. Chairs we will get to, but let me finish the rotating topic. Okay. So let's say I have the structure. Let's say I have a hydrogen here, methyl there, fluorine here, and then chlorine here, okay? So because okay, well, if we were to rank it by weight, chlorine is the heaviest, and then fluorine, and then methyl, and then our fourth group is hydrogen. Okay, so if our fourth group is on a line, like I said, we have to rotate. And how do we rotate is the question, okay? We rotate by redrawing everything, okay? You want to redraw all of your stereochemistry exactly the same, but all we're going to do is rotate the structure, the other atoms, okay? Groups, okay? So my goal is to have my hydrogen either on a wedge or a dash, okay? Now I can rotate as many times as I want, but it's simple just to rotate once. So I'm gonna rotate just to the right, which is counterclockwise, to get it on a wedge. So when I do my priority and then I get RRS, I can just simply flip it to get the correct answer, okay? So what I'm going to do is put hydrogen here, put chlorine here, fluorine here, then methyl there, okay? Does anyone have questions on just this part, like how I flipped it? Or sorry, how I rotated it, not flipped it. Okay. Okay, so that's good. I'm glad you guys are still with me. So if my hydrogen is on a wedge, that means I can do that. That means we're good. Okay, as long as it's on a dash or a wedge, that means we're good. Okay, so now that it's on a wedge, we're gonna do our priority again. So once again, chlorine, fluorine, methyl, hydrogen. So it looks like it's counterclockwise, but so counterclockwise means S, but because our fourth group is on a wedge, we have to flip it. Okay, so it's going to be R. Okay, and so you might be wondering, why do we have to flip it if, it's on a wedge? Okay, so wedge, I didn't really talk about this, but wedge means it's coming out of the page. Oh, sorry, let me put that right there. And then dash means it's going into the page. Into page. Okay, so you always want your smallest group in the back and into the page, and I'm not entirely sure why. The answer might be either in your textbook or your lecture, but you don't necessarily need to know like the science behind the reasoning. But if you definitely want to know why, I'm sure during lecture they might talk about it. If not, then don't worry about it. Just understand that the fourth group has to be um, uh, a dash, and if it's not a dash, it's on a wedge, then you have to flip it. Okay. So I know that was kind of confusing, but I promise you, once you start getting into chirality, whoever's here today or watching the video will get a much better grasp much quicker when you actually do it. Okay. Any questions before I move on to chair in the last 20 minutes? Okay. Actually, I'm gonna ask. Do you guys want me to do chairs or ice? Let me know in the chat. I got 2 chairs, 1 isomers. Anyone else? 2 isomers. Okay. Okay. All right. The chairs have it. Okay. I'm gonna clear the board, so make sure you have everything. And just in case you somehow didn't get to copy everything down, again, everything's recorded, so don't worry. Just go back and copy it down. All right. So chairs is something I don't like at all. So fair warning. Chairs, Newman projection, and Fisher, in my opinion, is some of the hardest topics in OCHEM. But after that, it gets much easier, especially for me personally, at least. And I say this because it's visually confusing, and especially because we are online, it's going to get even more confusing. So I'll try my best. Okay. So, sorry, give me 1 second. Okay, so I'm going to try my best to draw without messing this up. Okay. Oh, there we go. All right. Let me see how I can erase this. Oh, God, okay. Sorry, guys. All right. All right. Okay. Perfect. All right. So every vertice you see, once again, is a carbon. Okay. So all of these are your carbons, and they all have hydrogens on them. Okay. And then chairs are always going to be 6. Well, I don't want to say always, but the most ideal shape is going to be 6, because there are 5-membered rings and 4-membered or 7-membered, and those have different names like boats and half boats or flip chairs. But for now, we'll talk about the regular one, which are chairs. Okay. And chairs always change form from your standard hexagon. Okay. Not a benzene ring. Don't get that confused. The benzene rings have 3 double bonds. This is a cyclohexagon, or sorry, not cyclohexagon, cyclohexane. Okay, so cyclohexane, and this is a chair. Okay, so cyclohexane always has 6 carbons. Your chair will always have 6 carbons. Okay, unless it's like a boat, which obviously is not the same as a chair. Okay, so every vertex you see here, every vertex you see here is the same as, okay? And from what I've seen, and I personally like for this carbon to be number 1, number 2, number 3, number 4, 5, and 6, okay? So that is going to be the same as all of these, 1, 2, 3, 4, 5, 6. So let's say there's a methyl here, then there's going to be a methyl here. If there is a chlorine on carbon 3, there's going to be a chlorine on carbon 3. Okay, so vice versa. All right, so now that you guys have that down, I'm going to redraw this. I'm going to redraw this a little bit bigger if I can, without messing up. And there's no particular reason why that carbon has to be number 1. Well, first of all, it doesn't. Oh god, okay. I'm not sure why it does that line. Okay, that's not perfect, but it is what it is. All right, so there are 2 different positions on your chairs where your substituents can look like. They can either be in the axial form or the equatorial form, okay? And I'm going to note that in 2 different colors. The blue is going to be equatorial. Oh, okay. Blue is going to be equatorial, meaning it's going to be slanted. Sorry, I didn't quite draw this perfectly, so you have to bear with me. And then I'll draw all of your axial positions. Axial means, again, it's going to be up and down. This should be kind of familiar terminology with your hybridization and Vesper theory, I guess. So every time there's a vertex, you go simply up or down, and it kind of alternates. Okay. So once again, all of the red are axial. And this is kind of quote-unquote a template whenever you solve your or draw your own chair structure. And these are your equatorials. Have you guys covered this part, or is this also new? All right. Yeah, they might have not explained it in these terms, but this is how I like to explain it. Okay. Right, okay. Yeah. Well, okay, does OCHEM has live lectures, right? Or is it all asynchronous? Pre-recorded? Okay. Alright, okay. That's fine. So now there are going to be a couple rules I want you guys to note down, just in case I run out of time. The number 1, or I'll write the rules up here. Number 1, the bulkiest group is always always on E, and once again, E means equatorial. Number 2, 1, 3, Diaxial interaction is a big no-no. Okay, and I'll talk what that means. Okay, it basically there's something called steric hindrance, and that's when molecules collide with each other and it makes it unstable. Okay, and because chairs are like 3D version of a 2D cyclohexane, and in fact, let me write that down. This is 2D. This is 3D. Okay. So because we are changing this into 3D structure, we don't want our substituents colliding with each other, okay? Because they have something called electron clouds. And if those electron clouds bump into each other, it causes something called steric hindrance, okay? No, I'm trying to write that down. So steric hindrance, if you've never heard the term before, okay? All right. And then you guys already know it's derived from cyclohexanes. And then another rule, or not rule, but piece of information. Another piece of information is more carbons equals more stable. And what I mean by that is chair is more stable than a boat. Okay. And 6 carbons is the most ideal. I kind of went off the page, so let me bring it back right there. Okay. So I don't think you deal with 7 carbon 3D structures, but 6 is the most stable. You could see 5 carbons, you could see 4 carbons. 6 and 5 are the most common ones, 6 being the even more common one, but if you see a 5 carbon, that's going to be your boat. This is 5 carbons. This is 6 carbons. Okay. And then, so at the very beginning, someone said stability of chair conformation. Okay. So that means you will have to rank like 5 different chair structures or conformations by stability, 1 through 5. Okay. And part of that ranking trend is what we're going to discuss. Okay. And basically, less substituents equals more stable. If you have less substituents colliding with each other, obviously they're going to be more stable. As well as more E equals more stable. Okay, if you have more equatorial positions, they are also more stable. Okay, and we'll get into what that looks like with examples. Okay, now I want to discuss 2 templates. I guess before I move on, does anyone have any questions so far? You might still be a little bit lost, but hopefully if you guys seen lecture or went to lecture today, it might be connecting a little bit. If not, let me know. It's okay if you don't get it immediately right now, but I'll move on since no one has any questions so far. So I want to talk about 2 templates that you want to use, because the entire problem is before you even determine how to determine a chair is stable, you have to convert from a cyclohexane to a chair. Okay, that's half the problem. If you don't properly convert from here to here, then you won't be able to answer the question correctly. Okay, and meaning these substituents are usually wedges or dashes. They're not on straight lines. Okay. So let's say this is a wedge, and let's say this is a dash. Okay. So because I placed a wedge here and a dash here, these two might not be both axial. And in fact, chlorine here because the chlorine is bulkier. Okay. So just keep those in mind. So I'm going to draw two different templates. And I don't think they necessarily teach you the templates in lecture. This is kind of how I learned. I kind of just kept on teaching it this way. So I'm not sure if it's in the textbook or if a professor has taught it, but there are multiple ways to solve any kind of problem. So utilize everything that helps you. Okay, and this might be our last topic. So let's say you have all wedges on your template. Okay, if you're, and once again, your wedges and dashes together, that's called stereochemistry. So whenever we say stereochemistry, we're talking about wedges and dashes. Okay, so your stereochemistry is all the same. They're all wedges. So if they're all wedges, you can alternate by axial and equatorial. Okay. Or you will alternate. That's equatorial. This is going to be axial, equatorial, axial, equatorial, axial. Now, if your stereochemistry do alternate between wedges and dashes, in the first template, by the way, it can be all dashes also. It won't necessarily change anything. It could be all dashes or all wedges. That would still mean equatorial and axial alternate. But if it alternates in stereochemistry, wedges and dashes, then your other thing will be alternating. So let me finish this. Okay, so once again, if your wedges and dashes are alternating, then your equatorial and axial are all going to be the same. So either all equatorial or all axial. Oh, sorry. That should be equatorial. Equatorial. Okay, once again, these are templates to help you transfer your cyclohexane to a chair structure. Okay, so you probably have questions or don't exactly know what kind of questions to ask. That's fine. Let me do an example and hopefully this will make more sense. Once again, these are your two templates. So, and we don't necessarily have space and I don't want to clear the page, so I'm going to have to draw it right here. Okay, you have this, sorry, okay. Let's say you have a terp beetle at the very top. And terp beetle usually doesn't have wedges or dashes, or actually, no, it does. Okay, let's just assume it's a wedge, okay? If I can draw that. It's going to be reversed, but yeah, let's assume that that is a terp beetle, okay? If that is a terp beetle and then I have a dash methyl group here, and then I also have a dash second methyl, okay? So I prefer to use the first template. You can use either or. You just have to stick with one or the other when you convert all 5 cyclohexanes. Okay, so for now we're going to use the first one, Once again, the first rule is always to place the bulkous group on equatorial. And I haven't quite gone over that, but maybe in the next week review, I'll discuss more about chairs, Newman projections, and Fisher projections. Okay, so if this is equatorial right here, it's also on a wedge, so that's perfect. Okay, so now we have to look at, and it might help if you number these 1, 2, 3, 4, 5, 6, and then I have my dashes on carbons 4 and 5. And if I look on my template, I only have wedges here, right? And I chose to have this as a wedge, okay? So if instead of both wedges, I have both dashes, I am going to flip whatever I have on my template. So if it's supposed to be a wedge, but I have a dash instead of axial, I'm going to flip it to equatorial for carbon 4. And carbon 5, I'm supposed to have a wedge, but I have a dash. I'm supposed to have an equatorial, so I'm going to have a axial. Okay? So that's how you use this template to transfer to a chair structure. Okay? And I believe this is only like one of the ways. There might be another way that your professor or the textbook might recommend. So whatever way works for you, please go ahead. This is not, you only have to do my way or not. You just choose whatever works for you. Okay. And then before we end, I'm going to quickly draw the chair structure. Sorry, it's a little weird. Okay, so equatorial, remember, is going to be facing this way, and it's a terp butyl. And then on carbon 4, which is carbon 2, carbon 3, carbon 4, I have an equatorial. So I'm going to place a methyl that way. And then axial on carbon 5. So I'm going to place it directly up. Sorry, I know that's not the best chair, but this is how it should look like. Okay, so I have 2 equatorials and 1 axial methyl group up. Does anyone have any questions over anything that we've gone over? Because this might be still relatively new for anyone who hasn't seen it yet, or today is the first time, that's why you might be kind of confused, but I assure you, once you do more practice problems on e-learning and read the textbook or watch videos, it would help. Okay. Does anyone have any questions? If not, I can end the session here. Yes, of course. No problem. I hope that helps. Like I said, I know it's very confusing, but trust me, you guys will get through it. You'll all connect. Yeah, of course. I'm glad it helped. All right, I'll see you guys next week. Please feel free to join peer tutoring for drop-in if you guys want one-on-one help. I'll be in the lab tomorrow from 11 to 1:30. All right, see you guys.